So I'm Leonid Stolov, and I'm a PhD student in Institute of Biomedical Chemistry, and I will introduce you to a self-consistent classifier SAR approach. It is well known that ligand-based drug design is used in various drug discovery projects to facilitate the identification of possible hits and reduce the ever-increasing costs of finding new chemical entities. And every issue requires its own approach. The specified ASR approach strongly depends on the data used in the training set. And in a variety of cases, the experimental data is derived from multiple sources. It may occur that the resulting training set is highly heterogeneous and experimental values are obtained under diverse experimental protocols, and the attempt to consider their differences may lead to removal of significant part of the dataset or development of specified models for different parts of the dataset with low predictivity or low generalization properties. The altering approach is to use classification models. The data used for the training could be collected from both classification and quantitative experimental results in this case. And though a number of algorithms have been developed to satisfy the activity classification needs, the ability of the model to produce a generalized prediction is still challenging. And in this work, I will introduce the new approach to overcome the existing limitations. The self-consistent classifier ACR approach is based on previously developed procedures implemented in GUSAR software. And GUSAR uses quantitative neighborhood of atoms descriptors on one side and process them with self-consistent regression to develop quantitative classification, quantitative for classification models. Here are some consideration on self-consistent regression features. So first of all, the impact of each feature variable is restricted. That could be interpreted in terms of regression coefficients as the high values of regression coefficients are not likely to happen. So it may be assumed that these coefficients are somehow distributed. In this case, we assume Gauss distribution. And these parameters of these distributions produce additional restrictions, which could be regarded as regularization in the process of the training of the model. So practically, the regression coefficients have the parameters which correspond to their distribution and could be found with the maximization of a posteriori density, which could be expressed as the Bayes formula. And thus, this formula is composed of likelihood functions, and to estimate the parameters of the distributions of regression coefficients, we use the normally distributed values. GUSAR fits quantitative model development needs, but could be applied for classification model development, though. Based on self-consistent regression, two approaches were currently being developed. It is exponential and logistic self-consistent regressions for classification model development. And the main concept of these both regressions is to introduce a penalty function to effectively penalize misclassification and to consider the structures that are close to misclassification as the most important. Or otherwise, we assign them the higher weights during the process of regression coefficients estimation. For model development, validation, and prediction, we implemented the computational tools from scratch using C++ programming language and RCPP as a mediation environment to process the regression results. So how the probabilities are estimated in these regressions? Probabilities for the positive and negative examples could be expressed with a Bernoulli scheme. And in this case, we have just positive or negative cases. And for all the structures, we can calculate such a probability. And in logistic self-consistent regression, we additionally introduce the logistic function to get the resulting likelihood function. In this case, we have the plot for the probability, in the case of logistic regression function, we have the logistic function to penalize the misclassification, just like here. And it penalizes the misclassification in almost a linear manner. But if we can enhance it and use exponential expression instead to penalize in a more efficient manner. So and here we can compare the exponential and logistic regressions penalties. The exponential regression is highly stricter than logistic one. So when we perform these types of regressions, we make an iterative process with setting up weights and getting predictions, and then getting the estimates for regression coefficients. And the main thing that we expect is a stepwise convergency of the results. And here we can see the results for generated data, and during the iterations, they converge, weights and predictions, to some limiting value. Again, we made additional experiments with the generated data, and as we classified it, we have the information on the difference with the median activity. But of course, as the training said, we classified them as active or non-active. And as we can see here, the models calculated weights for them in that manner that structures that are close to the boundary of classes have the highest weights. And if the classification process is done well for the structures, then the weights are low. And in this case, this result just show the restrictions that were discussed above. As for real data, we performed the data collection from two different groups. The first one is the HIV data source, which is represented by three big data sets. The first one is NIAID database, which is freely available database with HIV inhibitors and HIV-related data. The second one is Campbell, which is also free available. And the third one is Integrity, the commercial database with pharmaceutical development data. All the data were combined, and the data for 3 HIV targets were extracted for integrase, protease, and reverse transcriptase. And were then used for model development. The other group of datasets is represented by TOX21 datasets. These datasets represent data generated from nuclear receptor signaling and stress pathway assays, and it was commonly used for different challenges. So from these datasets, we extracted 57 datasets with a varying number of structures from 3 to 5,000. And as for HIV data, it was classified based on the cutoff equal to 1 micromole, and TOX21 data set was taken initially classified. All the data was created before using the training set for the models. So for the HIV models, we made a comparison of exponential and logistic self-consistent regression with support vector machine models. And as the values of comparison, we took balanced accuracy and number of features used. And for validation procedures, we took, again, balanced accuracy, but for the data sets obtained during 5-fold cross-validation. And for here, we can see that the balanced accuracy is higher for exponential regression in comparison with others. But it should be taken into account that for support vector machine models, we took those features that were selected during exponential self-consistent regression model development. On the other side, for TOX21 models, we compared exponential and logistic approaches with initially taken self-consistent regression used for classification. And here we again compare balanced accuracy. We can see that in half by half, the balanced accuracy are nearly the same for exponential regression and basis self-consistent regression. But for the validation studies, for most of the models, so the results of cross-validation balanced accuracy for exponential regression have some advances. And in all the cases, the exponential regression used the lesser number of features that were used. So here we compare them in percent. So for all the 57 data sets, this procedure was done. As a result, it should be said that a new approach to the classification models development was implemented from scratch, and the different sources of data were used to build the classification models, and the different computational approaches were used and compared. And when validation and comparison of the models were carried out, the new models, logistic and exponential, but based on logistic and exponential self-consistent regression, showed the advances in dimensionality reduction problem. So they used the lesser number of features with the nearly equal performance in balanced accuracy. So I think thanks for the contributors which helped possible, and the support of the Russian Foundation for Basic Research. And thank you for your kind attention.
Thank you very much for the nice talk. Are there any questions in audience? Why is exponential penalty model better specifically for the cross-validation estimations? It's a question from Dmitry Shurga.
Sorry, could you repeat, please?
Why is exponential penalty model better specifically for the cross-validation estimations? You can read it in the chat if it is more convenient for you.
So the exponential penalty model, basing on the values of balanced accuracy, we can conclude that it is in most cases better than the models of comparison from original self-consistent regressions. Otherwise, there are some cases when it is not, but in all the cases, the lesser number of features were used. So the main assumption is that it is more generalized. It gives more generalized prediction when it uses a lesser number of features, but obtains equal or higher results.